Hello, everyone. I'm Siwei Zhang from ETH Zurich. So today I'm very glad to have this opportunity to present our recent project, the Egocentric Interaction Capture for Mixed Reality. This is a collaboration project between ETH and Microsoft Research. So with the continuous advancement of the augmented reality, virtual reality, and mixed reality applications, more and more immersive experiences are now enabled by the AR and VR headsets. And the egocentric view perception is the key to the AR and VR applications, as the sensors typically perceive the environments from the first-person perspective. So understanding the human behaviors from the egocentric view is a key element in this area. And as we can see here, the embodied camera motion and the close interaction distances between the humans and their surroundings can result in significant differences between the first-person view and third-person view visual inputs. And since existing datasets mostly focus on the third-person view data, models trained on them often fail on the egocentric output, for example, this post-estimation task here. And in order to fully release the potential of the mixed reality applications, it is crucial for the machines to automatically perceive the human motions, human interactions with each other, and with the surrounding environments from the first-person perspective. So to understand human behaviors during interactions, the first step is to estimate the 3D human body pose and shape from the visual inputs, especially from the egocentric view. However, research in this area is largely hindered by lack of data because most of the datasets focus on the third-person view. And such an egocentric dataset will be desired, and in order to capture such dataset, we need to know how to reconstruct the high-quality 3D human motions in 3D environments. So the question is, how can we capture the 3D human body pose, shape, and high-quality motions in 3D scenes? The traditional marker-based motion capture systems can usually recover highly accurate human motions, for example, the AMLD dataset. And the markers and the expensive setup make it quite impractical to capture human motions in everyday environments. As you can see, they usually require a specific studio and many cameras and to wear this specific marker suit. On the other hand, recently the procs captured the large-scale human motions in 3D scenes with a markerless pipeline by using only a monocular RGBD Kinect camera. However, the reconstructed motion can be really quite jittering and skating, and we can see it's not like really high-quality motions. So, with such a lightweight setup, how can we capture the natural and smooth motions in the 3D scenes? This is a quite challenging problem. And in order to solve these problems, I will present two of our recent works. The first one, Lemo, is a lightweight motion capture system to capture the human motions in 3D scenes with powerful motion priors. And with Lemo, we propose EgoBody. It's a large-scale egocentric dataset for 3D human motions, poses, shapes, and interactions in the 3D environments from the head-mounted devices. So first, I will introduce Lemo. Let's go back to the earlier question. How can we capture the natural and smooth human motions in the 3D environments with a lightweight setup, for example, a monocular Kinect camera? So in order to deal with, we propose to learn powerful motion priors from the high-quality mocap dataset, AMLD. Given a motion sequence, we first represent the body using a set of body markers on the body surface. And for each body marker, we compute its x, y, and z velocity for each frame in the global coordinate system. And we concatenate the velocities of all the markers of the current frame into a 1D vector as the body representation. By computing the body marker velocities for all the frames, we concatenate all the 1D velocity representation for all the frames into this 2D feature map, where each row here denotes the x, or y, or z velocity for each body marker, and each column denotes the specific time frame. So this 2D feature map serves as our motion representation. In order to recover the smooth and natural motions, we propose to learn a motion smoothness prior by training a fully convolutional autoencoder. And this 2D feature map serves as our input to this autoencoder. The autoencoder includes consecutive 2D convolutional blocks to encode the input into a latent space Z and the deconvolutional blocks for the decoding part. And the training loss includes the reconstruction loss for body marker velocity and a motion smoothness constraint which works in the latent space Z. So by penalizing the first order of the latent space, with respect to the time dimension, it can learn a latent manifold of the natural and realistic human motions. So instead of the traditional methodology of penalizing each joint velocity or joint acceleration separately, so which can degrade motion naturalness, this kind of latent space can capture a larger spatial temporal receptive field and captures the intrinsic full body dynamics. This is the visualization of the learned latent space of the input motions of this high-quality input motion from the AMAS in the left corner. So we can see that it's quite smooth. Then given a jittered input motion from prox dataset, for example, during the optimization, we first feed it into the pre-trained motion smoothness prior encoder. And then in the middle row, the latent space is quite noisy as well, as expected. So we enforce the same smoothness constraint over this noisy latent space to force the input motion to be close to the natural mass motions in the latent manifold. And then after the optimization, the latent space in the right corner is smoothed, and the input motion is also smoothed. So here are the results of our full pipeline on the prox dataset. This video shows that our method can produce temporal consistent and natural motions with accurate human pose and realistic human interactions. So we learn the novel motion priors from high-quality mocap dataset, which captures the intrinsic full-body dynamics, and we combine the motion priors into a novel multi-stage optimization pipeline to reconstruct the full-body 3D motions. And so to be specific, we use a monocular RGBD camera, and given a motion sequence from the RGBD video as input, and we have 3 stages in the optimization. The first stage, we fit for each body and for each frame separately, which results in jittered motion. And for the second step, we use the motion smoothness prior to produce the temporal consistent motions. And furthermore, in the last step, because there are some kind of body scene occlusions, which results in invalid body motions or skatings, so we train a motion infilling prior to recover those valid motions which are occluded by the scene objects. So with Lemo, we can acquire a lightweight motion capture system, and based on that, we extend it to the multi-camera setup. And we capture the ego body dataset. It's a large-scale egocentric dataset for 3D human body shape, motion, and poses of the interacting people during social interactions in the complex 3D scenes. So it has the multiple and synchronized data modalities from both the egocentric and the third-person views. Furthermore, we also provide the accurate ground truth for the 3D full body pose, shape, and motions in the reconstructed 3D scenes. And in the right video, you can see that the red dots denotes the eye gaze tracking of the camera wearer from the HoloLens. So to encourage the rich body motions, we define the social interaction scenarios from a classification from the sociology studies. And it spans diverse action types. So the various 3D scenes further incorporate more diverse human scene interactions. For the current stage, the dataset includes 68 sequences with 20 subjects in multiple indoor scenarios, and we are still expanding this dataset. So next, I will explain our capture setup. Given two interacting subjects in this 3D environment, firstly, we ask one of the subjects to wear a HoloLens headset to capture the first-person view images of the second person, and the eye gaze of the camera wearer is tracked by the HoloLens as well. 3 Azure Kinect cameras will capture the interactions or RGBD videos from the multiple third-person view. And given our multi-view RGBD videos and the HoloLens videos, we will reconstruct the 3D full-body shape and pose and motions of both interacting subjects by extending the earlier Lemo framework into a multi-camera and embodied camera setup. Next, we leverage EgoBody dataset to produce the first 3D human pose and shape estimation from the egocentric images as the benchmark. We can see from this table that the performance of the current state-of-the-art methods for pose and 3D human pose and shape estimation already start to saturate on the existing third-person view datasets, for example, the 3D PW here. However, when tested on our dataset, most of them show a very significant performance drop. This indicates that there are new challenges posed by the egocentric view data. So due to the constant motions of the embodied camera weared by the camera wearers, and also the close interaction distances between two subjects when they are really doing some social interactions with each other, the first-person view images can often exhibit very severe challenges such as motion blur or the severe body truncations here. And existing methods often fail on such scenarios because they are trained on the third-person view data. So we can see the incorrect predictions of spin and EFT of the body pose and body scale, etc. Here we show that the average error for each body joint tends to be higher if it's more frequently truncated from the images. Furthermore, we show that fine-tuning on our training set can improve the robustness of existing methods against these challenges posed by the egocentric view datasets. And quantitatively, our fine-tuned models show a much higher accuracy compared to their original models on both the pose and shape metrics. And finally, a cross-dataset evaluation can validate that our training set also can help the existing methods to generalize to the generic egocentric setup. So here we show that after being fine-tuned on the EgoBody training set, for the spin, metro, and EFT, which are the 3 current state-of-the-art methods, their pose estimation accuracy is improved very significantly on another egocentric dataset, which is the U2Me dataset. So to make a quick summary here, we present EgoBody, which is the first large-scale dataset for 3D human motions during interactions. And we provide very accurate 3D annotations for the full body pose, shape, and motions from both the egocentric and third-person views with the eye gaze tracking provided by the HoloLens for the camera wearer. So we present the first benchmark for the 3D human pose and shape estimation from the egocentric images, and we analyze the limitations of the existing methods and demonstrate the effectiveness of our dataset to provide further insights for future research in this category. And in order to capture such high-quality motions in diverse 3D environments, we present Lemo, which is a lightweight motion capture system for high-quality 3D human mesh reconstruction in the 3D environments. So we propose to learn the motion priors from the existing mocap dataset, and we combine them into this novel optimization pipeline to reconstruct accurate human pose and with the realistic human interactions. So that's all for my presentation today. And if you are interested, you are very welcome to look further into our project pages for further details. So thank you very much. I'm very happy to answer your questions.
Okay, thank you for your talk. Do we have any questions? So maybe let me ask you, it seemed to me that in most of these videos or samples that you were showing, it was mostly about a single person. Do you see multiple people interacting with each other rather as an opportunity or as a challenge?
Yes, so for this
algorithms?
data set, it's for 2 people interacting scenarios. So for the left video, it's 2 person because it's captured from an external camera. And the right video is just a single person because it's captured by one of the people by the headsets. So yeah. But yes, it's a future direction that we're considering to capture more people during like more diverse and complicated interaction scenarios.
Okay, thank you.
Yeah, thank you for your presentation. So you also capture like eye gaze here, and do you find any interesting thing in your like, data set about this like eye gaze part?
Yeah, for the eye gaze part, we did like some analysis, like to show some statistics, and we find that which fits our intuition, that during the interactions, for most of the time, the people's eye gaze or the attention of the people focus on the upper body. And yeah, it's just kind of an intuitive observation. And for the next part, I think we are going to use this eye gaze information to do some human attention prediction task.
Thank you.
Thank you for the presentation. The motion smoothness prior in the first work,
Yeah.
Does it look at the entire sequence for smoothness, or can it be used in a real-time scenario? Only looking into the past?
For the current stage, because it's an optimization, so it's not real time. So we have to input the entire sequence and then get the results by optimization iterations. Yeah.
Okay, thank you.
Right, any other questions? If not, let's thank the speaker.